Okay, we are ready to rumble here. Okay, so last day, and we didn't miss a day, so now I'm all thrown off. My other class, I missed a day, so I have to go back and do binomials with them. But for you guys, we haven't missed a beat, so I guess we'll just do review after this. I don't know. We'll see what I figure out for Wednesday. But for today, we're just going to finish regression. So if you don't have the chapter 7 notes, I still have 2 packages here. But I think you guys are all here. But make sure you have the chapter 7 notes and the assignment 7, which is due on Wednesday. You have the assignment 7. Okay. So let's see here. Oops. Can't write it all today. All right. So today we'll go through just, I guess, really the one and only example in chapter 7, because chapter 7, I find people are just kind of like, is that all I need to do? Are you sure? No hypothesis testing, no confidence intervals. It's just calculating the slope, the intercept, and doing just a little bit of tiny bit of math. It's a little bit different, right? But we'll go through the example, and I think what you'll find is that it's very similar to assignment 7, which you have to have in on Wednesday. And don't worry, it's very doable. Happy April Fools, by the way. Did you guys see the WestJet commercial for the Flyer Festival? It's really funny. You guys should really watch it. Because you know WestJet always does like a funny April Fools thing. Anyways, Flyer Festival. Yeah. Got it. Even I've seen it on Netflix, so even I'm in the loop. That's pretty good. So, as kind of a recap, we'll just kind of work our way through this example, but definitely by the end of it, you'll be able to do the assignment. So remember last day we talked about regression. We talked about the ins and outs of regression. We started with correlation. Right? Correlation is a numerical measure of the strength and the direction of a linear relationship. And so first thing we had to do was, if we have a scatter plot, let's pick a good one here, like this, right? We looked at, okay, well, what's the strength? What's the direction, and what's the form of this relationship? First of all, we're looking for a linear relationship. As long as you can't see a distinct curve in there, you can say it's linear, right? If it looks approximately like you could fit a straight line to it, you have a linear relationship. And then we said for the strength, well, as long as you see a pattern, right, at that point, it's considered strong, right? So as long as it's not random scatter everywhere on your graph, then that would be a weak relationship. But as soon as you see some sort of pattern here, then you have a strong relationship. You can throw in moderately strong if you want to, but I'm just going to stick to it's either weak or strong. And then if we have this downward negative relationship, of course it's negative. If it's upward, we have a positive relationship. And so we talked about those. We talked about the correlation. The correlation goes between -1 and 1. As you move out from 0, so a correlation of 0 means that there's no relationship between the two things. And then as you move out further and further to either -1, you have a strong negative relationship. +1, you have a strong positive relationship. Right? We said roughly once you hit the halfway mark, right, -0.5 and 0.5, that's where you transition from a weak to a strong relationship. But we just kind of did a fuzzy line there, right? So then we talked about, well, what did we talk about? Probably how do we calculate the slope and the intercept, and how do we construct this regression equation, right? Remember, y equals mx plus b. We have to find the slope, we have to find the intercept. We talked about the formulas that we're going to use, and we're about to use them now. But then we have this regression equation for us to use to predict new values using x to predict new values of y. So that's what we're doing here in this section. And then finally, we talked about R squared. R squared is just a goodness of fit measure, fun to say, easy to do. What could go wrong? It's just the square of your correlation. So it's just telling, okay, how much of the variability in your y values has been captured by this line, right? Essentially, how much of the activity on this graph, sort of, in a way, has been captured by your model, right? So you want a high R squared, because that means that your R squared is doing, or your line is doing a really good job of predicting new values. So for our example, we're going to keep talking about the percentage of high school grads and the percentage in poverty, right? So we have that data set that we've been talking about, and here it is again, where we talked about, okay, each state, in the states, of course, has some percentage in poverty where that's been defined. I think, I can't remember what the poverty line was, but anyways, so some percentage in poverty and then some percentage of high school grads in each state, right? And here's our data as far as describing this relationship, right? We said we have a strong negative linear relationship. Strong because I can see a pattern here, right? Negative because it's downward, and linear because, well, I don't see a distinct curve, right? So I can just fit a straight line to here, and it looks pretty good. So I've given you 5 pieces of information. So these are the 5 pieces of information that I'll give you on the final exam, right? And on the assignment, I make you work a little bit for it, right? Because I give you the scatter plot, and then I ask you to identify the response and the explanatory variable, right? But because you've got the scatter plot, right, the y-axis is your response variable, and the x-axis is your explanatory variable. So if I just give you the mean percentage in poverty and the standard deviation of the percent in poverty, that would be your y bar, and s, the standard deviation of the y's, and then the same idea for the percentage of high school grads, right? The mean percentage of high school grads was this with a standard deviation of this, right? So far in a blurb, that would be all this information, right? Here it's pretty clear and laid out for you. And then I also need to give you the covariance, which we denote S subscript XY, which in this case is negative 8.67. Any questions before we get to work? Yes.
When you're describing like strong positive linear sort of thing, you have to put that in a sentence.
No, as long as you list the 3 things, you're safe. Yeah. Cool. Good. Any other question? All right. I'll make a new page here. So can have some space. So we got example 4, part A. We have to find the, I'll just pull it up here. I think it's find the correlation, assuming. Oh, look at that. Find the correlation. Remember, the correlation is just R, but once you know that R is the correlation, then R is the covariance SXY over SX times SY. That's in the notes, it's also, I don't remember how the initial formula sheets I gave you were a little bit lacking. It's on the ones you get for the final, of course. But if you want to jot down the R formula on your formula sheet, that's a good idea. So here, it's equation, I kind of wrote around it, 7.1 R is S sub xy over Sxsy. Sure, I'll just steal this here. Why not? Do. Oof. We have all those three pieces, right? So there's not a lot that we need to do here. We just need to calculate our Sxy from our table was negative 8.67. The standard deviation of your x's was 3.73. And the standard deviations of the y's was 3.10. So I get 3.73 times 3.1, negative 8.67 divided by 11.563. You get negative 0.74980541. Just gonna cheat and round this to 2 decimal places. I would go 3, but it doesn't really make a difference. And I would just have to carry the 0 anyways. So we've got a correlation of negative 0.75. What I want you to do once you've calculated your correlation is just double check that it makes sense, right? One, it has to be negative if you have a negative relationship, vice versa. If you have a positive relationship, it has to be positive, right? So you want to double check that. But also remember your correlation goes between negative 1 and 1, right? So in this case, we've got a negative 0.75. Yeah, so it is strong, right? Because it's past negative 0.5 and it's negative because we have a negative relationship. So everything's kind of checking out. So there's a decoy question, Brett. I just saw your hand and then you're like, no. I was ready for a tough one. So now we've got our correlation, right? So our correlation is our numerical measure of the strength and the direction of a linear relationship. So it only applies because we have a linear relationship. Part B. Find the slope. All right. The slope from our notes here, our formulas. The slope is equation 7.3. Just copy. Oh. I can't erase that, it seems. That's okay. We have to calculate the slope first because the intercept, when we go to calculate it, we need the slope, right? So even though it feels a little bit backwards to find the slope first, we're going to find that we need it. So B1 is your slope. And on your formula sheet, right, it just says the least squares regression line is y hat is b sub 0 plus b1 times x with a slope b1 is r times sy over sx, looks familiar, and y-intercept b sub 0, y bar minus b1 x bar, right? So all those are on your formula sheet already. So we've got R and then SY over SX. We have the correlation because we just calculated it. We have the standard deviation of Y and the standard deviation of X because we needed it to calculate the correlation. Our correlation was negative 0.75, and the standard deviation of the Y's was 3.10 over 3.73. Here, right, they're both in the threes, so not that far off each other, right? Because we're both dealing with percentages of the same populations, right? So it's not that strange that they're similar, but it can happen that you have very different values for your SY and SX. And so it's very important that you keep track of, okay, SY has to be on the top and SY or SX has to be on the bottom, right? So that's why it's important to keep track of which is your X and which is your Y. Okay. 3.1 divided by 3.73, get negative 0.75 times 0.831099196. So I get negative 0.62332439.7, which is roughly, here I'll go to, I don't know, 3 decimal places. Negative 0.623. For the assignment, right, and even here, what you'll find is you'll use numbers from previous parts in the next parts. And so what you want to do is just, if you've rounded in this part, you can just use the rounded value for the following parts, right? You don't have to carry all these decimals. If you do, that's fine, and I'll know what you're doing, right? But we all like to round values. So, or I know you guys do. Can I round it? Can I round it? Yeah, now you can. So if you rounded it, you can just keep the rounded value. Okay? So we'll use a slope of negative 0.623. Okay? Any questions so far? I don't have any copies of the assignment, but if you're following along, I think that was part, what part was that? D? Thanks. Yeah. Yeah. So now, pretty sure the next part on your assignment as well is interpret the slope. So you find the slope and then you interpret the slope. And so here we go. For us, part C, oops. Interpret the slope. What you're gonna do here is to interpret the slope. Well, that's just taking the definition of the slope and interpreting in terms of this question, right? So what is the slope? The slope says that for each unit increase in X, in our case, X is the percentage of high school grads. So for each unit increase in percentage of high school grads, we'll see a slope, which is negative 0.623, increase in the predicted Y, which is your percentage in poverty, right? So you just take your definition of the slope and apply it to this question. Okay. So for each unit increase in percentage of high school grads, weird looking G, percentage of high school grad, which is your X, right, in general, we will see a negative 0.623, which is in general the slope, increase So I will always just use the slope and then increase, because a negative increase is a decrease. But if you wanted to take it that extra step further, you would have to remember to drop the negative, right? Because that would be a 0.623 decrease. So for me, it's just safer to always say the slope increase, because if the slope is negative, then the increase is technically a decrease, right? So it's just, you're playing it safe by just saying, okay, whatever the slope is, positive or negative, increase, you're always right. We will see a negative 0.623 increase in the predicted percentage in poverty, which is your Y. Any questions about that one? Good. All right. Part D says find the intercept. The intercept, remember, is where the line is going to cross the y-axis. And so let me just grab the formula here. It's formula 7.4 in the notes. B sub 0 is y bar minus B1 x bar. And so y bar and x bar, right? That's the mean of your y's and the mean of your x's. So it's just using the fact, and I think it's a pretty cool fact, that your least squares regression line will always pass through the point where x bar and y bar are. And that's just a fact that we're using. So I give you y bar, 11.35, minus the slope from before, negative 0.623, and then times x bar, which in this case is 86.01. Notice you'd be kind of hooped if you messed up 11.35 and 86.01, right? If you had those swapped, so you want to be really careful. But now, if we calculate these, you're going to have 86.01 times 0.623 negative. So you get 11.35 minus negative 53.58423. I get 64.93423. Roughly 64 point, let's say 93. So in part E, so a lot of these are just straight calculations, right? And then I make you interpret it, but just to keep you on the ball here. Part E, interpret the intercept, B sub 0. What is the intercept? The intercept is the predicted value of y when x is 0, right? So it's the predicted percentage in poverty when x, the percentage of high school grads, is 0. And I'm also going to add here, interpret B sub 0, so interpret the intercept, and then ask you, I'll make this a different color, a slightly different color. Is it meaningful? Because I think I asked that on the assignment. Okay. First, let's interpret the intercept, and then we'll talk about what it means for it to be meaningful. We talked about it last day, but That's okay. So the intercept of 64.93 is the predicted percent in poverty, which is your y, right? It's the predicted value of y, when percentage of high school grads is 0. Oh, percentage of high school grads, which is your x, sorry, I should have, is 0. If we look at our scatter plot and look at the range of our x's, what we'll see is that, okay, well, we've got x's from, I don't know, let's call it 75-ish to 95-ish, right? So our x's, our percentage of high school grads are somewhere between 75 and 95, right? So a percentage of high school grad of 0 would be somewhere over here. As far as it being meaningful or not, well, it looks like no states are going to have a 0% high school grad, right? But also, assuming that high school is still a thing, of course, then we don't expect to ever see a state with a 0% high school grad rate, right? And so it's not meaningful. Right? The line, remember, the line just keeps going and going and going forever. And so sometimes the intercept will be meaningful. So what I'm really asking is, can x be 0, right? And just kind of argue whether x can be 0 or not. In this case, it won't be, and so it's not meaningful. So I'll say, since percentage of high school grads, which is your x, will never be 0, the intercept is not meaningful. There are times, of course, where x can be 0, right? Things like temperature, that's an obvious one. Where's another one where x can be 0? And yeah, money, returns, speed, negative speeds, no. Yeah, fine. Acceleration. But there are some few instances, but a lot of the time, right, the intercept isn't actually that meaningful. It's just an anchor for our line, right, where it crosses the x-axis when it has to go there, right? And so it's just the predicted percentage in poverty when the percentage of high school grads is 0. Any other questions about that? Comments, concerns? No, keep going through the assignment. You got it. Yeah.
So it could be 0. You just say since it can be 0, it is meaningful. That's all you put.
Yeah. Because then that is your predicted value of y, right? So, all right, you said it. It's meaningful. Great. Moving on. Yeah, we don't go that deep into regression, so we're just kind of skimming the surface and then we get out. Yeah, because it's when x is 0, right? So how you find the intercept is when x is 0, right? That's where it'll cross the y-axis. But yeah, we don't look at the x-axis because it's not in the line. All right, find the intercept, interpret the intercept. Is it meaningful? Done, done. F. Find the least squares regression line of percentage in poverty as a function of percentage of high school grads. What am I asking for? I'm asking for y hat is b sub 0 plus b sub 1 x. We already solved for b sub 0 and b sub 1. We just plug those in. The whole idea of making this line is to keep x and y open, right? So that we can plug in whatever value of x we need to, and then find the predicted value of y. Remember, y hat is the predicted value of y. So what we have is y hat is b sub 0, the intercept was 64.93 plus negative 0.623 times x. Of course, 64.93 minus 0.623x. If you went straight there, that's great. Or if you prefer, right, because sometimes it's just easier to look at x and y as the variables that they are in this case, right? So here, y is the percentage in poverty and x is the percentage of high school grads. So what we can do is we can actually rewrite this and say, okay, well, or percentage in poverty, put a hat on that, a big hat, is 64.93 minus 0.623 percentage of high school grads. If you prefer to look at something like that, that's fine. I'm just going to stick to x and y because I'm lazy and I don't want to write that all out, right? But what you'll find in later questions is I'll say, okay, well, what's the predicted percentage in poverty, right? Predicted percentage in poverty, right? By putting a hat on it, it is the predicted value. So what's the predicted percentage in poverty when the percentage of high school grads is whatever? Then you just take that value, plug it in, solve for the predicted percentage in poverty. So, but if you just want to stick to x and y, that's fine by me. G's a little extra because figured I should refresh your memory on how to draw a straight line, but also it gives us practice predicting values and plotting them on our graph. So we do have a common final, and as it stands right now, I'm gonna see if I can swap it out for a different question, but as it stands right now, you're gonna have to draw a straight line on your graph. So that's why I figured I'd show it to you. I don't like it. I don't think it shows a lot of skill, but whatever. I'll see what I can do, but if not, just be prepared to draw a straight line. Okay, but what do we do to draw a straight line? Everyone's taken business math, maybe linear regression, or linear programming. Let's draw a straight line. So to draw a straight line, all we need is 2 points on the line, right? So we just pick two values of x, find the values of y at those points, draw them on our graph, connect those dots, extend the line, done. Okay. So I'll just make a note here. Draw the regression line on the plot. You only need 2 points. I think it's a little excessive to go for more than 2 points, right? All the points that you find are going to be on the same line, right? So as long as you have 2 points and you connect them, you're safe. So we need, I'll say, at least 2 points on the line. So what I'm going to do is, because I've given you the scatter plot here, I'm going to use values of X that are on here clearly marked, right? Things like 80, 85, and 90, just because it's a lot easier to deal with, right? I'm going to plug in 85, calculate my predicted percentage of poverty, put that point on here, right? Use 90. I'm only avoiding 80 because it's part H. So we'll do that one too. But so while I'm up here, I'll just steal this. You've got it. So. So what I'm gonna do, I just like to make a little table here. So I've got X and then Y hat is, I think 64.93, yep, minus 0.623 X. So I'll pick X equal to 85 and X equal to 90. Of course, if X equal to 0 is on your graph, that's an easy one to pick, right? Plug in X equal to 0, you've got the intercept, then you only have to find one more point. In our case, we're not so lucky, but then Y hat is 64.93 minus 0.623 times 85. Notice that we're using 85 and not 0.85. You always want to match whatever the data is that I've given you, right? So because the x-axis has 80, 85, 90, right, you have to keep it as a percentage. If it was 0.8, 0.85, and 0.9, then you would have to bring it down to a decimal. So you just want to match whatever the data is. But this is going to be 85 times 0.623 negative plus 64.93, 11.975. So that means that the predicted percentage in poverty, when the percentage of high school grads is 85%, is 11.975%. So what I'm gonna paste this scatter plot, and I'll say, okay, well, when X is 85, just see what I can do here. Not terribly straight, but that's okay. My Y is 11.975. Of course, this isn't going to be perfect because, well, I'm just eyeballing it and just drawing lines wherever I please. But 11.975, let's say it's somewhere here. So this value here is at 85, 11.975. Do the same thing for X equals 90. So Y hat is 64.93 minus 0.623, oops, 23 times 90. Times 0.623 negative plus 64.93, get 8.86. So for the next point, I'm at X equal to 90, so I'll just give myself a little grid here, and then 8.86, I don't know, let's put it somewhere there. So this is at 98.86. It follows my data, right? Because I was expecting to see this downward slope, and it looks like it's following the data. One thing that you can do is, even though I haven't asked you to draw the graph on the assignment, one thing that you could do is you could pretend to draw it just to make sure that it looks like it follows your data, right? If it doesn't, you've mixed up your X's and your Y's and you have to start over. All right, so now what you do, you've got these 2 points So you just take a straight edge, any straight edge. I usually just kind of bend over my page, use that, connect the two dots, right? So you just want to connect, take a straight edge and just connect these two dots and extend the line, and then you're done. So I'll just use formulas. Whoops. And it's a little bit hard to do on the iPad because it jumps, but it's okay. Let's see here. Didn't draw, did it? Still not drawing. Aha. Success. Not that straight, but And just to emphasize, I'll just say that this line has equation y hat is, now I can't even, 64.93 minus 0.623x. So all your predicted values of y will be on this line. And it doesn't matter what x you plug in, it's going to give you your predicted value of y. Good. So that's part G. Part H just says predict the percentage in poverty of a state with an 80% high school grad rate. So what we're saying is let x equal 80 and find y hat. That's basically what we did up here, but easier, right? Because we don't have to draw the line and we only have to find one point, right? And so now we're gonna let x be 80 and y hat is 64.93 minus 0.623 times 80. 80 times 0.623 negative plus 64.93. Y hat of 15.09. So then my predicted percentage in poverty when the percentage of high school grads is 80% is 15.09%. You can double check that that kind of makes sense with your line of best fit, right? Because if you plug in a value of x equal to 80 and you end up here at, does that look like 1509? Yes, it does. But you can't actually just use the line to do your prediction. You have to use your equation. Only because the line is only as good as we drew it, right? And here I'm all wobbly, right? And so can't use just the line, we have to use the equation of the line. Oh, snag my y down here. So when you're predicting, and I'm not asking, do you trust this prediction? Then you just do the calculation and then you're done. For part I, I'm saying predict the percentage in poverty of a state with a 50% high school grad rate. Do you trust this prediction? What I'm getting at here is we always want to check to see, okay, the value of x that we're using to predict our y, is it in the range of our data? Here, 50% is not in the range of our data, right? We looked at our scatter plot and we said, okay, somewhere between 75 and 95. Those are the grad rates that we've built our line on. Right? So when we go to a 50% high school grad rate, then we're extrapolating, right? We're extrapolating beyond the range of our data. It's still our best guess, so we'll still predict the value, and that's what we'll have as our prediction, but it's not a very reliable prediction because we're extrapolating. So same idea. Oops. We're gonna let x be 50 find y hat. And then do you trust this prediction? Y hat is 64.93 minus 0.623 times 50. 0.623 times 50 negative plus 64.93. Oof. Got a tickle. Just gonna grab some water. Sorry. I knew it was one of those that wasn't going to go away, so nipped it in the bud. Okay, so our predicted value of y, 33.78% in poverty. That's huge, right? Maybe I didn't. Oh well. But do you trust this prediction? No, I do not trust this prediction because we're extrapolating beyond the range of our data. No, I do not trust this prediction because I am extrapolating beyond the range of the data. So it's just a check-in point, right? Because whenever we're using these regression lines, they're only really reliable for the x's that we've built them on. Right? And so we have to check in, okay, well, if we're going beyond the range, then we have to make a note of it. Well, this estimate is not that reliable because I've extrapolated. Good. Part J. Oof, so many parts. But I find that they're all just kind of smooth sailing. Part J. What percentage of variability in the percentage of poverty is explained by the least squares regression line on the percentage of high school grads? That's a big lofty question, right? But what we're looking for is those key words, right? Percentage of variability. As soon as you see that, you have to think R squared, right? Percentage of variability. All I've done there is I've taken the definition of R squared. R squared is the percentage of variability in Y explained by the least squares regression line on X, blah, 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 right? But I can either ask for the R squared, or I can tell you 60% of the variability in Y is explained by the least squares regression line on X, and then I could ask you to find the correlation. In this case, I'm asking what percentage of variability, so we have to find R squared. Remember, R squared is just the correlation squared, which in our case was negative 0.75, and then square that. 0.5625 or 56.25%, right? What percentage of variability? So what's that telling us? It tells us that, okay, well, the percentage of high school grads is capturing 56.25% of the variability in Y, right? So it's doing a lot of explaining, right? But not all of the explaining in the percentage in poverty, which makes sense, right? We know that one thing is that these two things are not completely 100% correlated. Okay? And so, but a good chunk of it is being explained by the percentage of high school grads. All right. Any questions? No? So you should definitely be able to do assignment 7. I think there's no other curveballs on there. No? Great. So let's just keep talking about the rest of chapter 7, but as far as things you need to be able to do, that's basically it. Okay. So once we've fit a model, and usually we fit, 20 different models. I'll have mod 1, mod 2, mod 3, mod 4, and they're all just different little slight variations of each other. And then I go ahead and I look at brief things like the R-squared, right? I pick the one with the highest R-squared or the top 3 or whatever. And then I want to take it a little bit further to try to pick the best model, right? So the best line that I can think of. Okay. So R-squared is a really good just kind of measure of how well your model fits the data. But then we can also do things like a residual analysis. So remember, a residual is the distance between each of the observed points and the line, right? The line of best fit. And so the residuals tell us, well, how far are all these points from our line? Right? And we can analyze the residuals to check for things like linearity, constant variance, and, nearly normal residuals. What I find, though, is that a residual analysis, when you look at the residuals, it's more like a magnified version of your original relationship. Okay? And so the residuals, what you would have to do, if we go back to this scatter plot, right? Now you found the line. To find your residuals by hand, what you would do is you would have each of these XY coordinates, right, all in a list. For each X in your list, you would find the predicted value of Y, right, using your equation. And then you would make a new column of the residuals where you've got your observed Y minus your predicted Y. And those are your residuals, so you'd have to find one for each of these points. Of course, in R, when you use your LM command, right, to build your linear model, in your mod, I think most of you called it mod 1, because I did, right? So in your mod 1, let's say, play it safe, it'll store your residuals. So it'll have calculated your residuals. So you can actually do mod $1 residuals or something, resid, or can't remember what it is exactly, but it has your residuals there already. So you're definitely not gonna do them by hand. That's crazy. It'll just be another column. But that's what your residuals would be. Sorry. No worries. Did it say it's a lot of work? Because I felt like that was really appropriate. It's a lot of work. It is. So thank you. So first thing that we're looking for, right, is, well, do we have a linear relationship, right? We went out and we fit a linear model. We just want to make sure that we have a linear relationship. And so what we've got here over on the side is the top graphs. Oh, I'll have to zoom out. I can't write that big. These are your original plots. And these ones on the bottom, these are your residual plots. A residual plot just has your residuals on your y-axis. So your residuals is your response variable, and then your same explanatory variable as before on your x-axis. What you're looking for is random scatter around 0, right? You want some of these residuals to be below the line, some of them to be above the line, and you want them to be randomly around your line of best fit, right? So here for our residual plots, we're looking for random scatter around 0. So what you'll see here is, okay, well, here we've got this nice, strong, negative linear relationship. And so in our residual plot, right, we've got this random scatter around 0. It looks good. Right? Whereas here, we might seem to have this little bit of a curve. It's kind of iffy, right? But we're going to fit a straight line to it just in case. But we can see, okay, here some of them are below the line, and then for a good section of time, they're all above the line, and then they're below the line, right? So we've got this kind of slight curve, but it's just magnified in our residual plot that we do have this kind of curve, and we probably shouldn't be fitting a straight line to this graph. And then the third plot is supposed to show you non-constant variance. And so constant variance is just when you've got constant even scatter around your line. Right? Constant variability is even scatter around the regression line. So it'll look something like versus non-constant variability is when you have something like and then all of a sudden at some point things just get kind of out of control and you've got this kind of funnel going on. What's happening here is that the line would do a really good job of predicting values in this range, right, in this lower range. But then all of a sudden, these values, right, if we're out here for values of x, it's actually not doing that good of a job, right? So when we're using this line, we just want to make sure, okay, well, we want to have constant variance because we want to have the same reliability in our estimates for all points of x. Right? And if we don't, it's just something that we have to mention. So we can use our residuals to see if our model is doing a good job and if we have a linear relationship to start with. Our residuals, right, are the distance from the points to the lines. And so we want them to be centered on 0, but we also want them to follow a normal distribution centered on 0, right? Because we want most of them to be really close to the line, but then we're allowing for some of them to be a little bit further away from the line, right? But the majority of them are just kind of centered around 0. And you can just draw a histogram of the residuals, or even if you wanted to make a QQ plot of your residuals, that works too. Right, and look for this straight diagonal line, then you have a normal distribution of your residuals. And then we talked about constant variability up top. Any questions about that one? So as far as I can remember, the residual plots might be a multiple choice, like at best. Okay, so it's not something that you need to lose sleep over, right? But just kind of look it over. I'll warn you guys, I'll make sure, but I'm pretty sure it is a multiple choice question. Finally, we're going to talk about just outliers. What do we do with outliers? We're not going to dive too deep into what to do with them, but if we have a situation like this, where we've got most of our data down here following this nice linear relationship, it's nice and strong, right? We've got this kind of row operation over here, but it follows the general trend, right? So it's okay. But then we've got these 4 points making a mess, right? They don't look like data entry errors, right? So they're real data that we want to capture. And a lot of the time, we want to be careful when we're just removing the data points, right? I've seen that a lot. You know, friends doing experiments because they're in other fields or whatever. They're just kind of like, oh, well, I had these ones and they were no good, so I just deleted them. Okay. So you measured them. You're sure you measured them fine, but then you deleted them because you didn't like them? Okay. We don't want to do that necessarily, right? And so if we have points like this where, yeah, we've collected these happen, we want to be able to model those, right? But what might be the best thing to do is model those separately. So when you have things like this, so what you're going to do is you're going to fit the line with all your data points, right? That's going to be your jumping off points. Fit your linear model with all your data points just to see what your line looks like, right? If your line with all your data points looks like this, that's pretty good, right? Then you can just keep that, keep all your data points. You don't have to justify why you deleted some data points, right? It's a lot easier. But if you if you make your linear model, right, and it gives you a model like this, to try to model this relationship, I think we can all agree that that's not very good, right? It's not capturing these guys, right? It's under predicting these guys, and it's capturing just a little sliver of activity over here, but not the general pattern, right? And so what we do is you're going to remove the outliers, or remove them one by one, preferably, right? In kind of order of which one's the biggest or which one's the furthest away, and just kind of slowly pick them off until there's no real difference between your line with the outlier and the line without. Right? And so if your line changes from here to there, that doesn't really matter, right? As long as you can keep a little bit more data, that's good, right? And so you're going to look at things like the R squared. If the R squareds are essentially the same, then you can look at the residual plots, compare those, right, and pick the best model. But I would always argue that the more data you can keep, the better. But so that's how we handle outliers at the most basic level, is we fit the line with all our data, and then we remove each outlier one by one and refit the model until there's no real difference between the one with an outlier removed and the one without. Of course, in this case, right, where the line just kind of jumps around depending on if the outliers are in there or not, then we call it an influential outlier. We can also have high leverage, low leverage. I don't care too much about that. I just have it in there just so you have it, but it's not that important. Just like the mean and the standard deviation, because remember, the slope and the intercept, they're all hinging on the mean and the standard deviation. So the mean and the standard deviations are not resistant to outliers. Same idea here, right? If you have outliers, it's pulling the mean towards it, it's pulling the standard deviation towards it, right? It's just drawing everything towards it. And so your slope and your intercept are also not resistant to outliers. Right? And then the last thing that I kind of want to mention is just lurking variables. And it kind of brings us back to the R squared. We found an R squared of 56.25%, I think. Right, so 56% of the variability in our percentage in poverty was explained by changes in our percentage of high school grads. That means that there's other stuff going on there, right? Even though those two things are related, right? There might be other things that are influencing the percentage of high school grads and also influencing the percentage in poverty, right? And so those would be, bless you, lurking variables, right? Where, yeah, two things are clearly related, right? But there's some unexplained thing behind there, or that hasn't been captured in our data, I should say. So I just think it's so cute. I wish they didn't turn on that seatbelt sign so much. Every time they do, it gets bumpy. That's true. Probably a very nice, strong, positive linear relationship between those two things, right? But we understand that there's something underneath there. And so we have to keep that in mind, even with data that we don't really, truly understand. All right. Just like that, done chapter 7. Any questions? So you've got some time to finish the assignment if you want, but it's due on Wednesday. Otherwise, I'll see you guys on Wednesday or for the lab if you're not done.